very quick statements about magnetic boundary conditions, because again, I'm linking to stuff that we've done before, right? So the statements with Green's identities are contingent on the knowledge of boundary conditions in the regions of space where you're actually trying to compute the fields. So here, just a couple of words about the magnetic boundary conditions, really kind of repeating what we, some of the stuff that we had done before, but now just also lifting it to the vector potential. So we've already seen, right, that B above below is equal to, well, maybe we haven't seen it, but let's just discuss it. So this is the surface. Okay, so I'm just essentially writing the result here. So what do we have? We have a two-dimensional plane like that, in which there's a certain surface current K circulating. Okay, so K is really the now flattened version of our J. It's a J that takes values only in this thin sheet. And now you remember what we had also with the electrostatic field. That there was a surface charge density, there was a discontinuity in the normal part of the electrostatic field. Here, the same kind of logic occurs here. So you can do the same tricks that we used for the electrostatic field. You can use a Gaussian pillbox on this, and you integrate the divergence of B inside this pillbox, and you prove then that the perpendicular part of the magnetic field is continuous, because div B is 0, this whole integral is 0, and if I squeeze the pillbox, it's just the value of the field above the sheet or below the sheet, and that has to be the same. So that proves that the perpendicular bits of the magnetic field are just unchanged by the presence of that thing. And then the other thing I do, just like we did back then, we take a little Amperian loop here that straddles the boundary, and we integrate the curl of B on this surface here, and that gives us a line integral of the parallel component of B to that surface here, above and below. And this one, I use Ampere's law. If there is a current going through the loop like this, there will be a discontinuity. Okay, and that's how you derive this thing. So I would suggest for you as an exercise that you derive this boundary condition here from that logic, just to make sure you really understand this logic. Okay, I think it's a good exercise. So exercise for you, rederive this. From just starting div B is equal to 0 and curl B equal to mu 0j. Okay, you should have it, and really, you know, the kind of integral form of this. So K is just the current through that sheet. Okay, so you see it's absolutely parallel to what we had for the electrostatic things. For the vector potential, of course, it's a bit different, because the vector potential is like an integral of the field here. So you actually have that the value of the vector potential above is equal to the vector potential below. As usual, this thing, so the value of the vector potential is going to be continuous, but there's going to be a cusp in its derivative, because really I can understand this equation here as just a differential of the vector potential instead of the field. So you can just like rewrite that thing. And what you can see in the notes, it's the derivative with respect to the normal. I'll just write it like this and leave you to focus on this one here, and maybe just look at this one for fun. I'm not going to insist too much on this. Like this, okay? So you can check this. But what I would like you to be able to do is to rederive this equation here from div b is 0 and Ampere's law in integral form. I think that's a good exercise. For the A, I'm just stating these for completeness. Okay. Now the last thing I would then like to do today is the again. Oh, question. Sorry.
My question about the vector potential below and on the surface. So could you maybe clarify further with the drawing, maybe what you mean by vector potential being continuous, but the derivative being
so here, let me imagine a drawing where I've got the z-axis like this, okay, and this would be x, y, z, okay, and now I'm doing a slice. So here's my surface, and the vector potential takes a certain value, which, as I cross the surface, you know, maybe it takes a value like this, but then it starts off at a different slope. So the value itself is continuous, but the slope has a jump.
How could it be equal above and under the surface?
So here really, you see, maybe my drawing's not clear. So what I mean here with this line is the value that the A would take in the vicinity of the boundary. Yeah, so it's kind of rotated axis as compared to how you usually do plots, right? Usually you give me x and then f of x. So what I'm doing here is that there's z here, but here I'm giving you a of z. Okay, so my boundary is at this value of z, and as I come towards my boundary, my vector potential has a certain value which changes. But then at the boundary, you see, so the A above is this value, and the A below is this value here. So it's the same value in the limit, but the slope is different. So the function has a cusp at the boundary. Do you get what I mean? The magnetic field has a discontinuity at the boundary. So the magnetic field is going to go. So if you only have this boundary here, the magnetic field is going to go a certain strength, a certain direction below, and then suddenly, pop, it's going to go the other way. So there's a discontinuous value of the magnetic field.
I don't fully understand why this discontinuous.
Yeah, so one is the derivative of the other. So if you can have a discontinuous function at the boundary. So as you walk, it has a certain value, and then you hit the boundary, and then pop, it goes to a different value. You could also have a function that has a certain value, and then as you cross the boundary, it starts having a different derivative of that value.
I thought it was the x or the y direction, the first one, but I now see it's actually a. So yeah, I understand.
Yeah. Maybe I've just confused you with these extra things, but okay. To be clear, right? The boundary condition, which I think you really need to be comfortable with, is this one. Okay, what I'm telling you about the vector potential here, it's all nice, it's all very educational and whatnot. But the kind of real practical one is the one for B. Just mentioning the ones for A here, again, by saying things which, you know, are bordering on the too advanced, because we had seen Dirichlet, Neumann boundary conditions for the solution of the Laplace equation and whatnot. And now here, what I'm telling you is that the kind of natural conditions for the vector potential, they're also Dirichlet or Neumann of that form in view of the things that you have. And therefore, you would be able to use exactly the same uniqueness theorems that we've seen before, component-wise now, for all of this. But maybe that can sink in, you know, next year when you grudge about this course in one form. Oh no, but you have that. Yeah, that was useful. Question. Yeah, so here, so for example, in this case here, if my surface is indeed in the XY plane, then the normal direction is Z. So then it's really dz.
Oh, yeah, okay. Yeah.
And if you had like a sphere, yeah, with curved surface, and then you were looking at a certain patch somewhere, then there's a infinitesimal flat surface on this, normal vector like that, it's a derivative in that direction.
The other one is at minus Z or also
this is ddz above minus ddz below. So you're really taking, you've got the surface ddz here, you know, z plus epsilon, and then below it's also z plus epsilon minus. It's just you're taking the difference between this derivative and this derivative. But it's not like you do derivative here like that. It's really both derivatives you do the normal way. One's above, one's below, and you take value of this one minus value of this one. Okay? I think running out of time, next time I will entertain you, enlighten you with the multiple expansion of the vector potential. Just a couple of comments on it. Okay. Good luck.